Welcome back to our ongoing deep dive into the OEIS.
Oh, it's great to be back.
By now that it's just this incredible treasure trove of fascinating integer sequences.
It is.
And today we're focusing on one that's particularly relevant, I think, for number theory students like you.
Absolutely.
A000110, the Bell numbers.
Yes.
We've got both the OEIS entry itself and a Wikipedia article to help us unpack these numbers and maybe uncover some pretty surprising connections.
Looking forward to it.
Yeah.
So I think maybe the best place to start is, can you give us a quick refresher on what Bell numbers actually represent?
Yeah. So the Bell number B of n tells us how many ways we can partition a set of n distinct objects.
Okay.
So basically, you can imagine you have n different things. They could be numbers, letters, even your friends.
Right.
And you want to split them up into groups
Uh-huh.
where each thing belongs to exactly one group.
Okay.
B of n counts all the possible ways to do that.
So it's not just about splitting them up.
Right.
It's about counting all the different combinations of groups you could create. Yeah, exactly.
Can we see a small example just to make this more concrete?
Absolutely. So let's say you have a set of 3 friends.
Okay.
The Bell number B of 3 would tell us how many ways we can arrange those friends into groups.
Got it.
Turns out B of 3 equals 5.
Okay.
And we could have each friend in their own separate group, or we
Yeah.
could have 2 friends together and 1 by themselves.
Okay.
And there are 3 ways to do that.
Right.
And finally, we can have all 3 friends in one big group.
Okay.
So that's a total of 5 different partitions.
I see 5 ways I see it now.
Yeah,
So if I'm a number theory student,
right.
why should I care about this seemingly simple way of counting groups?
Because Bell numbers pop up in places you might not expect, even within number theory.
Okay.
So for instance, they have a really fascinating connection to multiplicative partitions of square-free numbers.
Okay, hold on. Multiplicative partitions.
Yeah.
I'm familiar with the idea of prime factorization,
Uh-huh.
but what does it mean to partition a number multiplicatively?
So it's similar to partitioning a set, but instead of splitting into groups, we're splitting a number into factors that multiply together to give us the original number.
Right.
So let's take 30 as an example. It's a square-free number, meaning it has no repeated prime factors. It has 3 prime factors, 2, 3, and 5.
Okay. So we're looking at all the different ways to multiply numbers together to get 30?
Exactly. And guess what? The number of different multiplicative partitions of 30 is B of 3, which we already know is 5.
Oh, wow.
So you think about it, we have 2 times 15, 3 times 10, 5 times 6, 2 times 3 times 5, and of course just 30 itself.
Yeah.
5 ways to partition 30 multiplicatively, just like the 5 ways to partition a set of 3 elements.
That's a pretty neat connection. I'm starting to see why Bell numbers might be relevant in a number theory context.
Yeah.
I thought they were just about sets and groups, but now we're talking about factors and prime numbers.
Yeah, it's fascinating, isn't it?
Yeah.
And this connection to square-free numbers and their multiplicative partitions is just the tip of the iceberg. Oh, no.
What's really mind-blowing is how Bell numbers connect to even more seemingly unrelated concepts,
Like what?
like equivalence relations and even rhyme schemes in poetry.
Wait, rhyme schemes in poetry. Okay, you've got to explain that one. How can counting partitions possibly relate to something as creative as poetry?
Well, think about what a rhyme scheme does.
Okay.
It divides the lines of a poem into groups based on which lines rhyme.
Uh-huh.
So if you have a 3-line poem,
Okay.
there are 5 possible rhyme schemes, just like our 5 partitions of a 3-element set.
Wow.
You could have all 3 lines rhyming, or the first 2 could rhyme and the last line be different, and so on, leading to 5 distinct patterns.
So the structure of possible rhyme schemes grows in the same way as the number of ways to partition a set.
Exactly.
Is there some underlying mathematical reason for that?
There is, and that's what we're going to delve into next.
Okay.
We'll explore how this seemingly simple idea of counting partitions leads to a deeper understanding of equivalence relations.
Which is a core concept in number theory.
Right.
And then we'll see how these numbers can even be used to analyze certain types of permutations.
Wow.
But first, let's take a closer look at how we actually calculate Bell numbers.
Okay, we've seen all these fascinating connections, but
Yeah.
how do we actually calculate these Bell numbers?
Right.
Is there a formula or a pattern we can use?
There are actually quite a few ways to calculate Bell numbers.
Okay.
One visually appealing method
Yep.
is using what's called the Bell triangle,
Uh-huh.
also known as Aitken's array.
Okay.
And it's constructed in a way that's similar to Pascal's triangle,
Okay.
where each entry depends on the entries above it.
I love visual patterns in math.
Yes.
How does this Bell triangle work?
So you start with a 1 at the top,
Okay.
and to get any entry in the triangle, you simply add the entry above it to the entry to its left.
Okay.
So the second row would be 1, 2, because we add the 1 above the 2 to the invisible 0 to its left.
Okay, so to get the third row,
Yeah,
we'd add 1 plus 2 to get 3, and then 2 plus 3 to get 5,
right.
which is B of 3.
Exactly.
Are you telling me the Bell numbers just appear along the edge of this triangle?
Exactly. The rightmost entries of each row in the Bell triangle give us the sequence of Bell numbers 1, 1, 2, 5, 15, and so on.
That's pretty crude.
It's a simple yet elegant way to generate these numbers.
Yeah. But is there a more formal way to define these numbers?
Yes.
Maybe using a formula?
We can define Bell numbers using what's called a recurrence relation.
Okay.
This means that each Bell number can be calculated based on the Bell numbers that came before it.
Okay.
Specifically, to find b of n plus 1, we look at all the previous Bell numbers from b of 0 up to b of n
Okay.
and combine them in a specific way using binomial coefficients.
Binomial coefficients.
Yes.
Those are the combinations we use in probability, right?
That's right.
The n choose k idea.
That's right.
Uh-huh.
So the formula might look a bit complicated at first glance,
Yeah.
but it essentially captures the idea that to partition a set of n plus 1 elements, we can choose some number of elements.
Yes.
Say k to be in a subset together,
Okay.
and then partition the remaining n minus k elements.
Right.
We do this for every possible value of k and sum up the results,
Okay.
using those binomial coefficients to account for the different ways to choose k elements.
So each Bell number depends on all the ones before it.
Exactly.
Kind of like how each row of the Bell triangle builds upon the row above it.
Uh-huh.
It's like a chain reaction of partitions.
Yes.
Our sources also mention another formula involving something called Stirling numbers.
Yeah.
Can you shed some light on those?
So Stirling numbers specifically, Stirling numbers of the second kind are another important combinatorial tool.
Okay.
That's closely related to Bell numbers.
Okay.
While Bell numbers count the total number of ways to partition a set,
Uh-huh.
Stirling numbers are more specific. They count the number of ways to partition a set of n elements into exactly k non-empty subsets.
So if I have to divide my group of friends into a specific number of teams,
Right.
Stirling numbers would tell me how many ways I can do that.
Okay. And the formula connecting Stirling numbers to Bell numbers tells us that b of n is simply the sum of all the Stirling numbers of the second kind for n, where k ranges from 1 to n.
Okay.
Essentially, we're adding up all the ways to partition the set into 1 subset, 2 subsets, 3 subsets, and so on, up to n subsets.
It's like we're looking at all the different levels of granularity
Exactly.
for partitioning a set, from having everyone in one big group to having each element in its own separate group and everything in between.
Exactly.
Yeah.
And for those who are interested in delving into the deeper mathematical structure, the OEIS entry even provides more advanced formulas, like Dabinsky's formula, which expresses b of n as an infinite sum,
Oh, wow.
and asymptotic formulas that describe the behavior of Bell numbers for very large values of n.
An infinite sum and asymptotic behavior, that sounds pretty complex.
It can get pretty involved.
But even for those of us who aren't diving into those advanced formulas,
Right.
is there something we can learn about the nature of Bell numbers from these different ways of calculating them?
Absolutely. One of the most interesting things these formulas reveal
Okay.
is that Bell numbers grow incredibly fast as n increases.
Okay.
The complexity of partitioning a set,
Yeah.
just like the complexity of rhyme schemes or equivalence relations, explodes as we consider larger and larger sets.
Wow.
It speaks to the power of combinatorial thinking,
Uh-huh.
how even seemingly simple acts of arranging and grouping can lead to an astonishing amount of possibilities as the scale grows.
So even though we started with this basic idea of counting partitions, it seems like we've uncovered a deeper truth about how complexity can arise from very simple rules.
Absolutely.
The rabbit hole really does go deep.
It does.
But before we get lost in the infinite depths of Bell numbers,
Yeah.
I'd love to hear about some of the real-world applications mentioned in the OEIS entry.
Sure.
What are some areas where these numbers and the concept of partitioning play a role? It's amazing to think that something as abstract as counting partitions
Yeah.
could have applications in so many different fields. The OEIS entry mentions connections to quantum physics, graph theory, even linguistics.
I know, it's fascinating.
It really highlights the interconnectedness of mathematics.
It does, and it speaks to the fundamental nature of Bell numbers.
Yeah.
You know, they capture something very essential about the way we organize and structure information.
Okay.
Whether we're talking about sets numbers or even, like you said, the lines of a poem.
So for all the number theory students out there,
Yeah.
what's the key takeaway from all of this?
Right.
Why should they care about Bell numbers beyond just their basic definition?
I think the most important lesson is that Bell numbers are a bridge between seemingly disparate areas of mathematics.
Okay.
We've seen how they connect to multiplicative partitions of square-free numbers,
Right.
a concept very directly relevant to number theory.
Uh-huh.
But they also pop up in fields far beyond that,
Yeah.
highlighting the unity and interconnectedness of mathematical ideas.
It's like those 6 degrees of separation games, but with Bell numbers connecting all these different mathematical concepts.
Don't I love that analogy?
They're the Kevin Bacon of the math world.
They are.
And for aspiring number theorists, I'd say,
Yeah,
exploring those connections can lead to some really profound insights
absolutely.
and a much deeper appreciation, I think, for the beauty and power of mathematics.
I agree.
So as we kind of wrap up our deep dive today into Bell numbers,
Yeah.
what stands out to you the most? What connection maybe surprised you the most?
Honestly, the connection to rhyme schemes never ceases to amaze me.
Really?
It's just this delightful reminder that mathematics isn't just about abstract symbols and formulas. It's a language that describes patterns and structures in the world around us,
Yeah.
even in the realm of art and creativity.
I completely agree.
Yeah,
It's a reminder that math is everywhere if we know how to look for it.
it is.
And for those looking to delve deeper,
Right.
there's a wealth of resources available, including, of course, the OEIS entry itself.
Yep.
But before we sign off,
Yeah.
I want to leave our listeners with a final thought.
Okay.
We've seen how rapidly Bell numbers grow.
Yes.
What does this tell us about the rate at which complexity increases as ink gets larger, whether we're talking about partitioning sets, rhyming poems, or analyzing more complex systems?
That's a great point. It suggests that as we deal with larger sets or more complex systems,
Yeah.
the number of possibilities explodes exponentially.
Wow.
And it's a humbling reminder of the vastness and the intricacy of the mathematical landscape
Yeah.
and the endless opportunities for discovery
Right.
that await those who dare to explore it.
So for all of our number theory enthusiasts out there, let this deep dive be a spark for your own mathematical adventures.
Absolutely.
Keep exploring, keep questioning, and keep diving deep into the fascinating world of number theory and the OEIS.
Couldn't have said it better myself.